Right. Right. I think the digital electronics and it's not in this part of the lab, it's out in the part that hasn't been developed yet, but this high school teacher that's been putting in his sensors, monitors and stuff. I think that would be a good place for maybe Sanford High School, Kingsland, if us to collaborate, getting that online, using the data. And Steve Gabriel, that high school teacher, just got me a bunch of more equipment for that area. So, and he's really happy. That's a collaboration.
It's just saying replace lane.
They're coming twice.
Working on third album. Yeah, working away.
So you guys get out early today?
Yeah.
So,
Is that every Wednesday?
Yep.
We have it's a smaller. I think we're gonna have a smaller. All my kids, the other one's gone. We have a large group. Start. Well, welcome. Just want to introduce and share with you. A few of you are here, so you've got a chance to see and understand. And we have some exciting things that we are looking at pioneering here at Kingsland. We are fortunate to have physicists from Sanford underground facility with a lot of research and share that with you. They're doing cutting edge, real world, exciting things that we're looking at relating to our curriculum and how we can be a part of that, what they're doing. So this is an introduction today of what they're doing out in Leeds, North Dakota. And the system we have, it's called an advanced Skype or an advanced Hangout. It's like real time, like right there. And we put this in to pilot this so we can start with sample research, but we also look at other entities that can be brought into the classroom, whether it's a biomedical class or engineering class. We can bring the world to you, work on things that you're studying real world. And that's a step above what's normally experienced in the classroom. So we're excited to share that with you. So this is introduction, but we will continue this through the rest of this year, where we will bring this in, whether you are in Mr. Ryder's classroom, or Mr. Brewer's classroom, or Mr. Moore's classroom, or Mr. Davis's classroom. We will be able to work and do some of these things that are pretty exciting. So with that, I'm going to turn it over to Dr. Laura. She came from Leeds, North Dakota. She's in the cities. We're excited to have her here. Yes. South Dakota.
Hi. So, my background's in physics, but I know most of you are in electronics and engineering courses here and in this group. And what you're going to see is there's a lot of engineering that goes into doing experiments like this. And they involve big teams of physicists and engineers from all over the world who work on that. So we're only going to be talking to one person, but he's representing like 100 people on that experiment. And I forgot to point this out the first time, but this is our modern understanding of the universe, that when you look out into space and you see the stars, that's only this really narrow wedge of this pie. And then if you add in all the rest of the stuff that we can see with ultraviolet telescopes, with gamma ray telescopes, with infrared telescopes, that adds in another 3.6%. So everything that we can see through the electromagnetic spectrum in the universe is thought to be only 4% of the universe. And the rest of it's divided up into dark matter and dark energy. And what we're going to talk about today is the dark matter part, because that's what they're looking for in experiments in the Sanford Underground Lab. And they're also looking for them up in Sudan. If you don't know if you're aware, there's some experiments in the lab, in the mine there, that are also looking for dark matter. The difference between the two locations is that they're a half-mile deep and we're a mile deep. So that makes our experiments a little more sensitive. And then also, we just have different kinds of experiments. There's enough of them that are looking for places to run underground, and I'll show you why in a minute, that there's room for labs in both states. So here's where we are, in the Black Hills. Way out here, anybody been to the Black Hills? Anybody been to Leeds? Couple? Yeah. So if you've been to Leeds, probably you'll remember the open cut. And that was the main part of the Homestake Gold Mine, which was started in 1876 by William Hearst and ran for 125 years until finally in 2001, the price of gold was so low and to modernize it was going to be so expensive that they decided to close it. And so at that point, they started the wheels rolling to try to turn it into a science lab, and finally they got federal approval to do that in about 2007. So we've been putting the lab together ever since. And this is the open cut, which is very large. It's like a 1/4 mile deep and a 1/2 mile across. And this is the Ross head frame. This is the Yates head frame, and those are the two surface parts of our laboratory. Under all this, there's 370 miles of tunnels that were built for looking for gold that go down 1.5 miles. So the laboratory itself, we're building at the 4850 level, so it's not quite 1 mile deep. And the bottom part of the lab is still totally filled with water. It turns out that every time it rains an inch, you get 12 million gallons of water flowing into this big funnel here and flowing into the mine. So they're constantly pumping water out and so forth. So here's just some pictures of over the years of 1877, what it looked like in its heyday of the 1930s, the 1970s. And in the 1960s, they put this first science experiment in. It was an experiment to look for this particle coming from nuclear fusion in the center of the sun called a neutrino. And it's the one thing that can get out of the center of the sun very quickly so that you can use it as a probe. The light actually takes 10,000 years because the sun is so dense. It takes 10,000 years for the light to bounce around and get to the surface. But neutrinos go right through all kinds of matter. They have no charge, and so they can come out very quickly. So Dr. Ray Davis, who's swimming in his water tank here, came up with the idea of putting a big tank of dry cleaning fluid 1 mile underground to look for these solar neutrinos. And this is what it looked like when we went back down in 2009 after that whole area was underwater. And this is what the detector that's in there, that same space now looks like. And that's what you're going to see today, except now it's in a big tank of water, so you can't actually see the detector itself. So the challenge is that these neutrinos, these little tiny particles that are made during nuclear fusion inside the sun, there's so many of them, there's 62 billion going through your thumbnail every second. So seems like a lot, but they're very, very hard to stop and study. They go right through the Earth. They go right through space, the sun. It would take a light year of solid lead to slow down and stop. If they wanted to stop when it's studied. So we can't build that. So basically, we build great big experiments and try to hope that maybe one in every trillion of them that come through will have some kind of interaction that we might be able to see. And the main background that we have, if we tried to do this on the surface, are cosmic rays. The cosmic rays come from the surface of the sun. They hit the top of our atmosphere and make big showers of particles. And there's about 1 a second that reach the Earth and go through your hand. But that's enough that it would totally drown out the signal. So that's why we have to go underground to do these experiments. And over the past several decades, people have been doing underground experiments like that. So here's all those miles of tunnels I mentioned. Here's that open cut. And here's the two head frames about 1 kilometer apart. So that kind of gives you a scale. The whole town of Lee is just on top of a whole lot of miles of tunnels. So a little bit about the evidence for dark matter. Why we think that 23% of the universe is dark matter. The term was coined way back in the 1930s. This astronomer, Fritz Zwicky, was looking at how galaxy clusters were moving deep in space with just a small optical telescope at that point. And he noticed that they weren't obeying the laws of physics, the gravity, 1 over r squared for gravity and so forth. They just weren't following that. And he surmised that there was a bunch of mass he couldn't see that was causing the movement. We all believe gravity, we understand gravity, and we know those equations. So we think the theory is that there's mass we can't see. So if you look in more modern telescopes that can look in the X-ray region, you see that between all these galaxies, there's actually a lot of gas. That was that 3.6% of that pie. Okay, but it still doesn't add up to enough mass to explain the movement of these galaxies. I'm sorry. And then another piece of evidence is in the rotation itself of the galaxies. They can measure the rotation because everybody's familiar with the Doppler shift, right? With sound waves, they change frequency if they're going, if the train's going away from you or toward you. Same thing happens with light. And if something is moving away from you in space, it's going to shift slightly its frequency of light, and they call that the redshift. So these lines, if they look at, say, hydrogen spectra deep in space, and then they look at exactly where the lines are, they can figure out how fast something's moving. So they used that, and they discovered that the galaxy doesn't rotate the way that one would expect the galaxy to rotate if all the mass is in the center. So we think the Milky Way, we're one of these stars out here on the arm, and the bulk of the stars is in that center bulge, and the center is a black hole, which has a lot of mass. And so most of the mass of this should be in the center, just like our solar system. Most of the mass is in the sun. But if you look at the solar system, the planets closest to the sun actually travel a lot faster than the planets way out. So it's stable that way. It keeps it stable. Whereas when you look at the galaxy, you're getting totally the opposite effect. If you look at a star inside, you're up here on this curve. If you look at a star way out, you're out here. So it's the opposite. So the galaxy really ought to blow itself apart. And they're surmising that it doesn't, because it's surrounded by this big halo of darkness, kind of this ball of dark matter just holding the whole thing together. So that's what they think. And every, well, if you had they think there's enough to hold the galaxy together, that if you had a 2-liter Coke bottle, you had 2 dark matter particles going through at about 200 kilometers a second. So they're just floating through our solar system, and what they want to do at the lab is to try to detect them. The one other piece of evidence is from looking at the Hubble Space Telescope images, and the fact that if there's matter in between us, our eye here, and a distant galaxy, then the light's going to bend around that matter. And they see these strange effects like these rings form, and that's a sign, they call that gravitational lensing, that the light is bending. It was predicted by Einstein, and you see it in these images. So there has to be something that's causing that light to bend and make that ring. So, and there's just another picture of it. And here's just some more pictures of the deep space images from the Hubble. And you just see all kinds of distortions. And so they figure that's all caused by dark matter. And they can actually use supercomputers now and calculate from all those distortions what the distribution of dark matter would be in 3 dimensions in a little swath of the universe. They take a little piece and they can calculate all that out. So what is dark matter? Well, there's been a lot of theories. One is that they're super tiny black holes floating through our universe, and they've looked for them and they can't see them. So the one that most people think is the most probable now, and the one that most of the experiments are looking for, is assuming it's a particle called a WIMP. So we have T-shirts at the lab. They say "Nerd searching for WIMPs." That's kind of our slogan. So WIMP stands for Weakly Interacting Massive Particle. So basically, it's a particle that has no charge, so it doesn't respond to electricity and magnetism. It does respond to gravity, and it does respond to what's called the weak. We hope it responds to this weak force. Otherwise, we're never going to see it. But we're assuming that it does. So it's similar to a neutrino, but orders of magnitude more massive than a neutrino. So I'm going to switch over to the Davis campus here, but I'm going to just orient you. When you come out down the cage, basically it's like a mine. Anybody ever been down a mine that had an elevator? Yeah, very dark. In ours, there's water dripping on you. It's a 10-minute ride. You're wearing your mine gear and all that. And then you get down and you're like in a very modern science lab. You walk around the corner from what we call the station, and you have to go through and wash the dust off your boots, take off your coveralls and your hard hats and everything that's dusty, because that would be a problem for the experiments. And then you go through the door into this science lab. So we have the camera set up in here where the Lux experiment is, large underground xenon, searching for dark matter. And at the end, we'll switch quickly over to this big area, which is a huge clean room where they're making the world's purest copper and using it to build a demonstration experiment for a neutrino experiment. So we can't really talk about that, but it takes too long for today, but it's really impressive, so take a quick look at it. So here's just that thermos I showed you that was the Lux detector is basically xenon, which is a noble gas that's been cooled down to be liquid. So it runs very cold, and if one of these WIMPs come through, here it comes, and bumps it head on, it can give off a little bit of light, and it'll give off a couple of electrons. And these squares on the top and the bottom are photosensors that look for that light. Okay, and so they use that signal to try to determine that that's really from some unknown particle called a WIMP and not from other things that might be kind of like neutrons coming from radiation in the walls or things like that. So that's one reason they have it in the big tank of water, is to get rid of that background radiation. So we're going to switch now. You there, Mark? Yep, there he is. Let me just switch the video.
Okay.
Okay, we have you on.
Hi. All right. Oh,
We have a
you ready for-
smaller class this time, so introduce yourself. Most of these students are taking digital electronics or bioengineering. Yeah, so a couple of engineering courses.
Excellent. All right. Well, as Peggy said, I'm
And
Mark
a few
Honhart.
of them were here. Go ahead.
Well, I'm sorry. I think we've got a delay. All right. So I'm Mark Honhart. I'm a physicist here at the lab. I'm also a PhD student working on the Lux dark matter detector. So this is kind of my wheelhouse, what we're looking at here. I suppose just to introduce you to the lab itself, the detector that Peggy showed you in animation before, that she showed you inside the detector, that is below us about 10 or 15 feet inside of a 72,000 gallon water tank filled with ultra pure water that we use for additional shielding. You can probably see behind me some of the aspects of the detector itself. In this section, this stainless steel looking stuff, the cylinder on top there, that's mostly our cryogenic system, and that's what we use to cool our xenon down to the point where it can be a liquid. We use liquid nitrogen, which is 77 Kelvin or about 200 degrees below 0 Celsius. So very cold, very intricate electronics that we have to use for that. Over here we have a lot of pumping systems that we use to circulate our xenon around and purify it so that we don't have false signals coming from some sort of impurity in the xenon. And then, of course, you may see up here a lot of electronic systems that we use for really running a lot of the pumps, running a lot of the valves. And then we have, I'll flip the camera over here so you can see these. We've got, you can see here 4 of our computer racks and electronics racks. And we have lots and lots of electronics in here running analysis on our waveforms on the data we're actually getting from our detector, and a lot of computers analyzing it and parsing the data so that we can use it for actual analysis later. We also have a lot of similar computer racks on the surface that are doing similar things, and then a lot of computers at other universities that are running real in-depth analysis. So there's a lot of computing and a lot of electronics that goes on with Lux. We also have, let me see if I can switch the camera over here. There's, as much as there is on the top level that I'm standing on now, there's even more stuff down that stairs. There's a lab for working on our gas system and our cryogenic systems, and a lot more electronics down there. So it's one experiment with about 100,000 different parts working on it. So it takes a lot to keep it running and keep everything happy. So it's interesting working down here because some days you're a physicist, some days you're a mathematician, and then there are days where you're a plumber. So it's an interesting variety that you have to deal with down here. So I'd love to answer any questions you guys have off the bat.
I'll just second Mark on that last comment. When I first started in the field and got my graduate degree and went on to get my first job, my mentor the first day said, well, the best background for this job is auto mechanics, because it was all plumbing, vacuum systems, things like that. So,
Yeah.
Questions? Yeah.
I have a quick question. You guys mentioned that the facility you're working in is a mile underground versus the one that's getting half mile. How does that, would they be able to conduct the same, you said there's similar dark matter experiments, but is that increase the efficiency of your equipment being that far under, or is that just not the convenience?
Yeah. The question was a half mile. I mentioned that Sudan was a half mile and we were a mile. So he was just asking about the differences. And you worked at both, so why don't you mention?
Yeah. Yes, I did work at Sudan for quite a while before coming here. It's actually a considerable difference. When we're down, say we're down more than half a mile, the main thing we're concerned about is muons, because most of the cosmic rays that are generated in the upper atmosphere by the sun, they won't penetrate more than 5 or 10 feet. But muons are a really insidious form of cosmic ray. because they can penetrate very, very deep. And even here, a mile underground, we can't block all muons, but we can block a lot of them. I think we block all but 1 out of 10 million, so that's a lot of them. But at Sudan, because it's an exponential kind of drop-off, I think at Sudan we were blocking 1 out of every 10,000 or 100,000, so it's an increase of almost 1,000-fold. It's a lot quieter. But of course, for these particular experiments and their particular sensitivity, a mile is definitely better than half a mile, but a half mile we could have made it work. We're definitely in no danger of real interference from muon signals down here.
So there's always a trade-off when you're designing an experiment like this between cost and the first thing you always want to be as deep as you can, and especially the bigger the detector gets, the more sensitive it is. So as you build your detector bigger and bigger, it becomes more important. So they have to consider all of that. Yes.
So if something were to malfunction out there, would it set you back 7 years from the beginning? Or would you be able to fix it, like obviously not completely, but it's like for a long time?
Yep. So Mark, she had a question about if you had a malfunction on the detector, would you have to start all over from 7 years ago? Or would you be able to, I guess it would depend a little bit on what happened.
Well, you know, we've got backups for backups for backups for just about every part. So we could have a real catastrophe and it may set us back a year, but probably no more than that ever, really. It certainly would be bad. I mean, we don't want something to happen, but we really, the 7 years that we spent getting everything ready was really us understanding how to build stuff. I think that if we were to have a real disaster, we could probably rebuild all of this inside of a year, now that we know how.
Right. So a year and a half ago, they had to figure out how to move this from up on the surface to underground, and it became a real major engineering problem. And because they didn't want to do any damage to the detectors. So the scientists said, you can't tip it more than 1 degree, and you can't jog it more than 1 G, which is very little force. So they basically spent months and months figuring out the best way to move it underground. If you actually go onto our YouTube channel, there's a neat time-lapse video of the actual move, but they ended up getting these air hockey skid things to actually move it because the train tracks were too rough and there were all kinds of issues. So it really, the engineering that goes into just supporting it even after the physicists had designed it, a large project.
One last question regarding the depth. I noticed in the cutaways of the mine that it actually goes deeper. Are there is there a need, or are they discussing going deeper with some of these experiments, or just kind of holding fast where you're at?
Yeah, the original plan for the lab, when they first proposed it to the National Science Foundation, was to also develop a campus at 7400. Right now, the National Science Foundation is not doing it. The Department of Energy is, and they don't want to spend the cost. It's tremendously more expensive. If you remember that map, the shafts kind of ended at 5,000 feet. In order to go deeper, there's an internal shaft, which they call a winze. I learned all kinds of mining terms when I moved from Berkeley, California to South Dakota. But there's a winze that they would have to totally renovate, get those hoists working again. And so it would be millions of dollars probably.
Okay.
So,
And more water to pump.
and yeah, well, they could pump the water out. They're keeping it level right now at 6,000 feet because it's a lot easier to not have to maintain those lower tunnels than to have to, keep them up and ventilate them. And I mean, if you think about the engineering, just the ventilation of 370 miles of tunnels, and like there's things like radon levels that they worry about for the detector, and they were working on shafts a couple of weeks ago, and it was really cold, so they decided to cover the shaft so the workers would be warmer. The radon levels in the lab, a mile and a half away, shot up like 3 times. So there's just like all of these different things interconnected that you have to worry about every aspect of operations. So, I think we're almost out of time. Any other quick last questions?
How come they decided to use xenon instead of some other substance?
He's asking about xenon rather than any other substance.
Oh, okay. Xenon we chose for a couple of different reasons. First of all, it's a noble gas, which means that purifying it is really easy. We can put it through a pyrophoric metal that interacts with anything that's not really a noble gas. So anything that's not xenon is taken out. It's also there's availability. Xenon is something we can get, and even though it's very expensive, it's something that's available. It's not really exotic. But having an inert gas like xenon is ideal because we don't want to experience some sort of weird chemical reaction going on all the time inside our liquid, which would happen with just about any other substance. Whereas a noble gas like krypton, nothing's happening. It's totally inert.
So there are some dark matter experiments, though, that are using like argon gas. So that has slightly different properties, and so it might be more sensitive to maybe, they're guessing what the mass of the WIMP is, and so different experiments are sensitive to different parameters. And so there are multiple experiments around the world. Do you know how many there are dark matter experiments running right now?
I'm aware of at least 30. It depends on the level you cut off between professional and amateur experiments. I'm sure there are a lot of people out there who are looking for dark matter who are working without,
probably with
full
their
university
cell
back.
phones.
Yeah.
So,
Sure.
I found a cool website where they were measuring cosmic ray muons with cell phones, which I thought was pretty cool.
Very cool.
All right, well, I think we better quit. It looks like it's about time, right?
Very last question that you have for Dr. Clark. And as you see the technology that we have, this is the on-site, so on. We're going to bring this into the classroom and work with Sanford Research. There's other groups and so on from the medical profession we're looking at bringing in. As you can see yourself in the upper right-hand corner, Mark sees himself the same way, and you appear as a big picture like you're watching Mark, him. And so we have that at real-time presence and the quality to be able to bring this type of education into our classrooms. So this is an introduction of more to come that we'll be able to do this year. We're excited about that.
And I think the other positive here is you heard from underground that you need to be a jack of all trades. So, there are professions there to support organizations like this that tie very well into digital electronics, into the pure sciences like physics and chemistry. So again, it opens up, I can think of the biomedical research that could take place underground because a lot of places are doing some of that. So
Right.
a lot of opportunities here for those interested in that career.
Yeah, we were looking at the possibility of collaborating with your digital electronics class and getting some monitoring data from underground that you guys could use for doing experiments with. So I think that would be fun. So we're going to talk about that more this week while I'm here. So thank you. So thanks, Mark.
Thank you, Mark, for Biology.
So I appreciate you giving up your lunch hour.
No problem. It's always fun doing this.
Okay. Talk to you later.
Bye.
Wonderful. No, it's very little delay. It's
got my talk on it. That's fine. If you ever want a picture from it, you can grab it.
I'll meet you guys there. I'll be out of
This is still recording. Do we need to turn it off? Yeah, I think so. Is it that? No, that's the. Yeah.
perfect. And that's what I was wondering, what would be the application?
Oh, it is?
I just want to find a restroom.
He is.
Yeah.
Right.
You help point me toward a restroom, and I'll be right back.
Okay, sounds good.
It was a long drive.
Yeah, probably you or.
I mean, just because I don't have, this is what I'm doing up here, is I'm just
Probably
using
work.
this.
I'll probably have her,
This mic right here,
Okay.
and then what I did right here is I'm gonna remove this.